So there's actually an exciting Mars mission, probably launching later this year, called ESCAPADE, or Escape in Plasma Acceleration and Dynamics Explorers, that's being headed by UC Berkeley and supported by Advanced Space to look at Mars's magnetosphere. And to talk to us about this project is Mitchell Rosen. He's the Astrodynamics and Satellite Navigation Engineer at Advanced Space. Mitchell?
My name is Mitch Rosen, and I'm going to be ESCAPADE, a mission that is launching to Mars later this year. First, a little bit about the team. We have the team at Advanced Space, which includes myself, Jeff Parker, and Andrew Keeler. We are working on the trajectory and maneuver design. The team is led by UC Berkeley. They are the PI and PM. Dr. Rob Lillis there is with the Space Sciences Lab, and they are doing the science for the project. And Rocket Lab is building the satellite bus. So a little bit about the story of ESCAPADE. The concept started in 2016, 2017 when NASA requested a study to understand planetary science and what could be done on a low budget. At the time, they projected a budget in the range of $110 million. So we converged on 3 low-thrust satellites in the range of just over 100 kilograms each at that time. In 2018, Simplex was announced, and the budget was half of NASA's guess from the prior year. So this caused some changes in the mission. We cut down to 2 satellites and made them a little larger, and we intended this as a rideshare with Psyche. The following year, we were selected and funded under heliophysics. The satellites have continued to evolve since then. We're currently at a wet mass of 530 kilograms each, so we've grown significantly. Part of the reason for that is that in 2020, the Psyche launch was changed, and we were projected to go very far over budget. So we had to demanifest from Psyche and ended up switching to high thrust in an effort to reduce the expected budget of the mission. In 2023, we were selected for launch on New Glenn, and we're currently projected to launch later this year. So as you can see, we've had to be very nimble with this project. Things have changed constantly and rapidly. And that's a big part of having a low-cost robotic mission to Mars like this. If we want to be able to do low-cost missions in the future, we need to be able to react to changes fast, because things are in this space change very quickly. So a little bit about what this mission is for. I want to preface this by stating that I'm an engineer, not a scientist, so I will do my best. But yeah, any questions on this, I might defer to Dr. Lillis at Berkeley. So the goal of this mission is to investigate the composition of Mars's magnetosphere and the escape process of ions from the magnetosphere. There's a few regions of the magnetosphere that are particularly interesting, particularly boundaries between separate parts of the magnetosphere. The reason that we're launching 2 satellites named Blue and Gold for Berkeley's colors are that they want to be able to study both temporal and spatial variations in the magnetosphere. So you might know that MAVEN is doing relatively similar science to this, but it's only 1 satellite. Having 2 satellites allows us to take simultaneous measurements at different points within the magnetosphere and compare them to each other to see how things change. So a little bit about the timeline of the mission. So as I mentioned, we are set to launch later this year in late September or early October. We're taking about a year to cruise to Mars. We will arrive one after the other at Mars in the beginning of September of 2025, Gold 2 days before Blue. Following Mars orbit insertion, we're going to have an orbit reduction process where we get from the orbit we insert to at Mars down to the science formation with a period in the middle where we are not maneuvering while we wait for solar conjunction to finish. Then we'll do science campaigns A and B, which I'll talk a little bit more about later. And we expect to close out the mission probably sometime in 2027 is currently the plan. So I personally worked on the orbit reduction and transition to science formation phase of the mission. So I'm going to talk just a little bit about this, some about the complexity and some about how we've had to be nimble in the design. So as you can see, we take a lot of steps to get from the initial orbit that we're entering Mars at down to the science formation. You can see on the left, we're looking at periaps and apoaps radius, and on the right, we're looking at some of the orbital elements for this 2 spacecraft. So the reason that we're taking so many steps is to reduce the risk that we significantly under or overshoot our targets, because we are a small mission. Funding-wise, we need to accept some risk, but this is a way of reducing a risk to make sure that we don't put ourselves in an unrecoverable position. We're also using what we can about Mars's gravity field to our advantage. So on the bottom right, you'll notice a graph about the node. Basically, instead of ever directly targeting this element, we're actually using Mars's gravity to help us. So the goal by the time of science is to have the two satellites in the same orbit, just separated by approximately 20 minutes. So there's an inherent drift rate for certain elements, and you can see that in the bottom right, they come together by the beginning of 2026. We time our maneuvers early in this phase so that that happens by itself by the end of the end of the phase. So this is just a little zoom in to show a little bit of more detail. On the right side here, you can see when we are doing the second half of our transition to science, we come into this part where we need to look at the lead time. So it's how many minutes ahead of gold blue passes through its periaps. And as I mentioned, we want to be approximately 20 minutes ahead, but there's a high level of sensitivity here. So yeah, we just need to be very careful in how we perform all of our maneuvers. Some other things we've had to consider include eclipses. So the satellite buses being built by Rocket Lab are built to handle approximately up to 75 minutes of eclipse time. As I mentioned, we've had to make several changes to the ConOps over the course of the mission design. One of them was we noticed that we were seeing eclipses upwards of 250 minutes at one point in early 23. So we had to make significant changes to this part of the mission in order to avoid these eclipses that would have effectively ended the mission. We've also had to think about close approaches, not only between two satellites, but between the satellites and each of Mars's moons. As you can see, we're not too concerned about getting close to Deimos, but Phobos is a big concern for us. We've had to keep a really close eye on it throughout the process here. We are definitely going to be getting close. We're not too worried about Phobos' gravity having a significant impact on us, as much as we're worried about direct impact with it. So eclipses and close approaches are two of many things that we've had to keep a very, very close eye on throughout the design of this mission. And then a little bit about the science campaigns. So you can see that campaign A, the two satellites are in effectively the same orbit, and campaign B, they separate so that gold is higher than blue. As I mentioned, we're going to be looking at temporal and spatial variations in Mars's magnetosphere. So this is the reason for the separation between the two campaigns, to allow for varied study over varied regions. So just to connect this all back to the point of the conference, humans to Mars, as we start sending people to Mars, we're going to need a lot of robotic support missions there at the same time. There's going to be a lot of things that they need, whether that's communications, whether it's robots in orbit that are helping them with science studies. So it's super necessary that we are able to conduct low-cost robotic missions to Mars to support people on the surface. So $55 million for a two-satellite mission is very low. If you include its extended mission, that's something like 10% of the cost of Maven. So we've learned a lot about how to reduce costs for missions and how to be nimble and be prepared to make changes as they become necessary. Also, of course, an improved understanding of the Martian environment and the interaction of Mars with heliophysics is super important for understanding what will be happening to astronauts on the surface of the red planet. Yeah, that's all I have. I think I could probably take one question if anybody has one.
Thank you, great presentation. I was just wondering, where are we now as human beings using autonomous rovers and autonomous, like the systems that you're actually working on for troubleshooting without the help of the humans right now?
Yeah, that's a great question. Thank you. I cannot say that I have a great answer to that question. Not a lot on this mission is autonomous, unfortunately. We're going to be designing each of the maneuvers on the surface and sending them up to the satellites. But I know that there are others within my company who are doing a lot to work on autonomous mission design, and I'm sure that we'll be seeing missions flown at Mars in the near future that autonomously design things, such as maneuvers and conduct science autonomously. Thank you.